I gotta edit that. I'm gonna have to edit that recording. Yes, absolutely. Absolutely. A little post-processing is needed. So first off, does anybody have any questions on anything so far? Homework or anything? I know one person did the homework and said it was not too bad. It kind of is. It absolutely is. Yeah. I don't think it should be too bad. What did you think that maybe the hardest thing was in it? Like that maybe people would have trouble with was
maybe like the composition proof or the whatever the thing with the X and a little squiggly and Y.
Yeah, we're going to talk about that today for sure. So, okay, cool. Yeah, yeah. But the composition proof, do you have it written down, like what the problem was? I just want to.
G composed with F is on too.
Yeah, can I just grab this really quick? So let's talk a little bit about one of these problems. We have, just to get you rolling, which one was this? Do you remember? Oh, okay, cool. Yeah, maybe. Oh, yeah, it does. Yeah, good. It's on the other page. Cool. So if G composed with F is on 2 and G is 1 to 1, show F is on 2. Let's talk about that because it might have been a while. And you're like, yeah, that could be challenging. So let's talk about this one. So first off, we need to set some stuff up here because we don't even know what these are. So first I would anchor myself with some notation. I'm going to say that f is a function that maps from some set A into some set B, just so I have something to think about, right? Write down some things like what are these functions? What do they do? And then G, where does G have to eat from? B. So F takes input from A and spits it out into B, and then G eats that because, right, this is G eats F of X. Composition works that way. So this must map from B into some we don't know. That's the only way this could possibly make sense here. So now we have that set up. So we're going to assume this is the case. Now we know that G composed with F, so G composed with F maps from A into C. Let's draw another little picture here. So we got A, B, and C. So F does this, G does this. All these pictures help. They help the thought process and thinking about how to throw pens or whatever, drop them. Okay, so now what else we've got? We've got G composed with F is onto. So let's translate that into something we can use. What does that mean?
For every element of the code C, there is at least one corresponding element in the domain.
Yeah. Notice how I'm slowly taking the definitions and just writing down what I've got. I haven't even thought yet, right? I'm just writing down the definitions and hoping that I start to see things. It's like in physics or whatever, chem, where you got to cancel units. So you look at all the units and you're like, okay, what's going to cancel here? And that helps me guide my way toward things. I'm sure there's more intelligent ways to do it. If you're a chemist, I'm sure you don't just try to cancel things out and you actually understand what's happening. No? Oh, okay. No, okay. It's all about canceling units in the end. Cool. So what this is saying, let's draw another little picture. Here's C, it's a set of things. Here's A, it's a set of things. Every one of these pictures helps me. And then in the middle, I got B. So now G composed with F does this. Let me put my B up here. So if I've got some C here, for every C in this output space, there's some A over here that hits it with G composed with F. So every output you give me over here, I can find an input that hits that with the composition. But how does the composition work? The only way this could happen is if there's some intermediate B that first, let's see, what is that? First F hits, then G hits. That's the only way that composition can move from A to C, if there's some intermediate element, B. Does that make sense? Okay. So now I've taken G composed with F is onto, and I've got all sorts of stuff going on here. I've got a little picture that I'm going to use. I also know that G is 1 to 1. So G is 1 to 1. Let's put down some of our definitions for 1 to 1. Let's put down both versions of it. So there's two versions. First off, so let's see, G moves from C to B. So here's C, and here's B. And G does this. So G 1 to 1 says G doesn't do this. Don't write that down because that's like hard to interpret. But it doesn't take two different things and send it over here. What I do know is that if I have two outputs over here and I have G of A, and that's actually equal to G of B, hold on, let's do G of B equals G of B prime. And then over here, I've got B and B prime. That the only way these two things can get sent to the same place is that they're the same in the first place. So if G of B equals G of B prime, if the outputs are the same, the inputs have to be the same. They can't be different. That's what 1 to 1 means. Then B equals B prime. So this can't happen unless these actually were the same thing to begin with. What is the contrapositive of this statement? All right, it's logic and proof time again, right? So logic and proof says if P, then Q. So this is my conditional. What is the contrapositive? I'm big on contrapositives, right? Like I feel like every class, Sophie, yeah. So you're thinking of, yeah, that might actually, yeah, I'd have to translate this. I think that probably is true. But what's the more easy to remember version? Yeah, that might be true very much. Just how do I flip this into an if then? Do you remember that one? I think you're right. If not Q implies not P. So the contrapositive is if not Q, then not P. So that little symbol there is my not symbol. Let's talk about this for a minute because, and I've talked to you all about, some of you have heard this conversation many times, my little light switch thing, but damn, it's good. So P, in this original statement right here, P is a switch and Q is a light bulb. And I'm going to draw an old man light bulb, like incandescent. It's not an LED. It looks like it's like an old school. Edison made that shit. And this is Q. So if P then Q tells me that if P is active, if P is true, close that switch, the light comes on. So here's power source over here. This is if P, then Q. And Q is the light comes on. If switch is flipped, then Q, the light is on. The contrapositive says, if the light isn't on, then the switch can't be flipped. It's saying the same thing. So the contrapositive says, if the light is not on, then switch P is not flipped. It is false. It is in a state of falsehood. These are the same thing. They tell us the same information. So that's how I do contrapositive. It's looking at the inverse of the situation. So what is the contrapositive of that statement there? Camila, what's the contrapositive of that? Thank you so much. So the version, this is the straightforward version. The contrapositive says if B is not equal to B prime, in other words, I have two different inputs, then G of B is not equal to G of B prime. If I have two different inputs, they get sent two different places. That's one-to-one. No two things get sent to the same place. And that's super important, apparently, because they're telling us we need that information here. So now, what do we got to prove? We need to show that F is onto, that if this whole map from here to here, the composition is onto, and this G is one-to-one, then this dude here must be onto. So here's how we're going to roll with that. How's that proof going to look? And I hope this is helpful. I hope this is reminding you of some things, or maybe you haven't seen these things before, possibly. That could be possible. So we need to show. Always write these things down. I've got like a PhD, right? Right. Hope. So I say. So the legend goes. I've fooled everybody. I've got a PhD in math. I'm still doing all this work. You should be doing all this work. You do not have a PhD in math yet. You will. You might. But not yet. And if I need to do all this to think about this, you do too. So don't cut corners and slow down and back off. What do I know? Write it all down. What do I need to demonstrate? Write it down. So what I need to show is that F, which goes from B to C, A to B. Wait, is that right? Yes, F goes from A to B, is onto. And what we mean there is onto B. It hits everything in B. There's nothing in here that I can't find an input for to hit. You tell me something here, there's an input over here that gets me there. I don't know. F might not be one-to-one. I don't know. I don't know shit about F. That sounded like you were clapping or something. There's a little clipper. But I do know G is one-to-one, and I know the whole map is onto. So somehow we have to piece this apart and dissect it. All right, so B is on to B. So what does that mean? I need to show this, i.e., take any little b in B and show there is some little a in A such that F of little a equals that B. Are you with me? Any questions on any of this? Okay, so First, I'm going to take a little b and b. And let's see, how do we get? So now we got to make the move. And I even have to think about this for a second myself. How do we take our other information and move it? So let's make some clear space over here. All right, so we're going to show F is onto B. So I'm kind of writing a more formal proof here. I'm going to take a little b and b. I'm going to draw my pictures out again. So here's B, A, C, and now I got little b. So G composed with F is onto, and G is 1 to 1. So then F, let me draw my functions. F does this, G does this. And I know that this whole composition is onto, and that is G composed with F, and that is onto. Okay. Huh. So Christian, you did this. Did you approach by contradiction?
I haven't gotten to this part yet, but I was going to say contradiction feels like the way to go. Because if you
Yeah.
like, if G of F is onto and G is 1 to 1, then F is not onto, and like start with like F is not onto.
Yeah.
I think that'd probably be the best way to go, because then you get like the contradiction with G being 1 to 1, yeah, and then like hitting everything in like the C group or like codomain would be impossible to.
Yeah. Let's try that approach first. I like that. So here's what we're going to try to do. We're going to try to contradict this. We're going to show that if this is true and this is true, and we make this false, in other words, F is not onto, then we have a contradiction. So this may or may not work. We're just going to do it together. Let's proceed by contradiction. My main goal in these first few days was to review some things, and that's what we're doing. So we're going to proceed by contradiction, i.e., we're going to assume, and like I said, I don't know, this might not be fruitful, but we're reviewing contradiction. Assume that G composed with F, which goes from A to C, is onto, and assume that G, which goes from B to C, is 1 to 1, but F, which goes from A to B, is not onto. Now, if F is not onto, what would that mean?
It means that there's an element within B that is not mapped to, like F does not map to every element in B.
Beautiful. Yes. So if F is not onto, there's something here that I can't hit. And let's call that this B that I've drawn up here already. So i.e., there exists some B in B such that F of X is not equal to B for all X in, or we could say A. Let's just say that, for all A in A. So I can't hit this guy here.
Can you then just say that?
Oh, yeah.
It doesn't work because it's 1 to 1.
Yeah, there's something, because G is defined on all of B. G can eat everything from B. We've already assumed that. So G takes B and does something with it. I'm trying to figure out whether 1 to 1 might come in. So let's see. Oh, yeah.
Does 1 to 1 have inverse? So like,
if we're on 1 to 1 and onto, we have an inverse. Yes. Yeah.
Wouldn't the contradiction come in because if it's 1 to 1, then each input in B has to have its own output in C, and if there isn't a way to get And if we put in B, then we can't.
That's it. Yes. Yes. Perfect. Yes. Okay, cool. Let's do it. Let's pull it together. That's it. Oh, that's it. Resolution. Beautiful. Okay. So I can't hit that. There's nothing in here that I can shove into F, a very technical term, and spit out B. But I know that G is defined on all of B. And so if I pick something over here, let's take a C. So, but since F composed with G is onto C, for any C, little c and big C, the set C, there exists an A in set A, yeah, that'll work, such that F of little a equals that C. So if I pick this, and I know this whole map is onto, for this C, I can come back here and find that A. And then this A through this map goes there. But that means G must also hit that C, because this whole map actually says feed here, then feed here. So let's pick it up on the left side of the board. If someone wants to try to do a direct route on this, that would be so cool. Like without contradiction, a direct proof. Because I was like, my brain was kind of reeling on that a little bit. And that's why I was like, okay, let's try contradiction. That might save the day. All right, so keep writing the proof. Okay, so for any C and C, there's a little a and a such that F of C equals. This shouldn't say. This should say F composed with G. Sorry. Fog of A. F composed with G of A. Is it golf? It's golf, not fog. Thank you. G composed with F. Golf of A. I.e. G of F of A equals C. But G maps from, is that G goes from B to C, and G is defined on all of B. So there exists some, wait, am I saying, okay, I feel like I'm jumping ahead there, because now I'm like assuming F. G of, wait a minute, okay, hold on, let me back up. Or let me stop. If you see the next move, let me know, because I think I got my wording wrong here. G composed with F. F. Okay. Sorry. So this is good. So G goes from B to C. So this F of A, let's come back to this, i.e. G of B equals B prime equals C, where B prime is an element of B. So this must first go here to B prime, and then it must go to C. There's an intermediate step there. But how am I not? Oh, because I said I couldn't hit C, right? Was that what I assumed?
Yeah, because if it's 1-to-1, but we can't get to that B from A, then there wouldn't be any way for G of F to get to that corresponding value.
That's right. That's right. So there exists to be such that F. Yeah, I don't like the way this proof is going, though. is because we've already set up, there's this B in set little b that we can't hit. So how does that come into play? Because we said this was the B we can't hit.
You had for any C in C, there exists an A where A goes to C.
Yes.
And then you, because to get from A to C, you have to go through B. So you said there has to be a B prime in B that gets you to C.
Yes.
And so therefore you'd have to be able to hit every B in B. Is that our next step, or can we not jump through that?
But why?
Because G of F is on to.
Yes. Or oh, yeah, I wrote that wrong. Were you going to say something, Kayla?
I was going to say that.
Okay. Or that back there. Yeah. But how do I bring this B in that we can't hit? That's what I'm not seeing here. Like, this proof is falling apart a little bit because I said,
That was your assumption.
yeah, that was my assumption, that the guy I can't hit is this little guy right here. Oh, but whoa. Oh, go ahead. Yeah, go ahead. I think I maybe see what we need to do.
If it's injected, can you assume that the size of the domain and codomain need to be the same?
Not necessarily. If they're infinite, it could be just like, yeah. And yeah, we don't, because if they're infinite, we don't necessarily have to have that. Yeah. But if they're finite, I think that is true. All right, so let's get this shit out of the way. Okay, so I assumed I couldn't hit this little b, but G is still defined on that B. So maybe my problem was that I jumped too fast to the C. I think that is my problem. All right, let's do it again. Let's come back. Let's back up just a little bit. F can't hit that. So F can't hit that beast, but G can eat that. G can still eat that. So let's make G of B equal to C over here. And I think that's the move. That's the move right there. So, okay, so let's go through what we've done. We're proceeding by contradiction. I assume that G composed with F is onto, so I can hit everything in C with the combined maps, with the composed maps. Then I said, but wait, F isn't on 2. So there's some little b, some intermediate b here that this F can't hit. No matter what input I put here, I can't hit that. But G can still eat that dude. But G is defined on all of B. And so there exists some B, let's just call it B prime because there's too many freaking B's floating around, in B, such that G of B prime equals C. And that's this guy right here. However, I can hit this with the composed map. But since G composed with F that maps from A to C is onto, there exists some, oh yeah, this is coming together, this is great. There exists some little a prime in A such that G composed with F of little a prime equals that C right there. So coming back, this was the C, and this is the little a prime that I can shove in and get through the whole composition. But what does that mean? Let's write out what this means, i.e. G of F of a prime equals C. And now the one-to-one is going to kick in. So we already know that
So we know that f of a prime cannot equal the
B.
only possible output that lets G of something.
Yes, that's exactly, yes, that is 100% it. I'm just trying to think, what's the good language here, right? That is exactly the contradiction. But f of
like f of a prime does not equal B, and
did I make it B prime? Yeah, like B prime, yeah.
yeah,
For any A prime, and there's not another one because G is one-to-one. Because G is one-to-one, there's no two different things that could hit that C in the first place. So, and G is one-to-one, so there is no other B in B such that G of B equals C. See, this seems so ugly, what I'm saying here. What's the elegant words to take us there? Okay.
because f of a prime does not equal B prime, G of f of a does not equal B prime, so we have a contradiction. Does not equal C.
Yes, 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 yes. Okay. Wait, say that again. That was good.
It would be since f of a prime does not equal B prime, G of f of a prime does not equal C, so we have a contradiction.
Oh, yes, because G is one-to-one. Yes, yes, beautiful. Thank you. It's the contrapositive. It's the freaking contrapositive version. Yes. If I have two different inputs for G, I have to get two different outputs. And so that cannot equal C because that was an output of it. And that contradicts what? What is that contradicting?
Contradicts G of f being onto.
Yep. Awesome. Whew. Wow. Kind of glad we talked about that. So your goal is to make that prettier than I have. And your goal is to understand it. And I'll know you understand it because it'll be pretty. Camila, you have a question. I see your brows. Yes. Yes, because remember, so does that make sense?
Yeah.
Yes, ma'am. Yeah, perfect. Yeah, yeah. I can always count on your eyebrows. Been doing that for years. Do we feel like we... I know, I'm going to sit down tonight and mess with it and try to get a direct proof. If somebody comes up with a better proof, please go for it. That would be great. I feel like there must be a direct proof, but it's kind of escaping me at the moment. What was that other problem that we were going to talk about? There was a different one. What was the second one? Cormac, you?
Oh, just the stuff we were going to talk about today.
Oh, yeah, equivalence. Cool. Oh, you ready for some new stuff? Yeah, okay. Oh, you guys, it's just lovely people. Just being nice. Okay. Let's talk about equivalence relations. Don't forget, when you do write up your homework, please include a facsimile of the problem statement that conveys the pertinent info. That would be great. Okay, this is really quite abstract, but one of the key constructions in mathematics. It's modeled off equals. It's based on equality as you understand equality. We all know, and I know you might feel like you don't know much right now. Sometimes after a proof like that, you're like, well, I don't know anything. But you do know this. We all know how equals works with numbers. With real numbers. A, B, C, those are real numbers. So that's an element of the real numbers. Is that notation okay with everyone? All right. We know a couple of things. We know that every number is equal to itself. 3 is equal to 3. Thank God. Things would get weird if it wasn't. I don't even know what the world would be. We'd be collapsed into some weird little black hole. And I know that if A equals B, then B equals A. Seems reasonable, right? It's kind of got that flip. Like if I said to you, X equals 3, that's the same thing as 3 equals X. Those mean the same thing. The same information is conveyed. And I also know that if A equals B and B equals C, then this B links the A and the C together, and they must be equal. Then A equals C. So these are the 3 properties of equality that we're going to model this new structure off of. And how many people actually saw these in Logic and Proof? Kind of. I feel like we don't do it heavy, right? And some profs skip it entirely. So if you haven't had Logic and Proof, you're on key with like almost everybody else in the class on this. This is called reflexivity. So this is reflexive. Equality is reflexive. Anybody know what this one's called? Symmetric. Yeah, you can flip the sides. This is symmetric. Equality is symmetric. And what is also this guy? Transitive. And it is transitive. We're going to take these 3 properties of equality and generalize them. That's what an equivalence relation is. So an equivalence relation is generalized equality. And it can be created for things that aren't numbers. They're just mathematical objects in a set. So let's talk about that. And I'm going to show you some ways to think about this that I don't think our book shows you at all. And many books don't show you. I'm going to give you a little picture to draw when you're thinking about these things. Several pictures to draw. So let X be a set. I've got this collection of things floating around, and so I would draw a circle and call it X, but I don't think that's going to buy us much. Let X be a set, anything you want. And equivalence relation on X and let me just make sure I'm not missing any fine details of this. Yes, is a relation R on X denoted, and I'm going to define the word relation, so just hold on, denoted by the symbol tilde such that, and we'll come back and we'll do relation in just a second because it's pretty straightforward, just kind of means subset really, is a relation on S denoted by the symbol tilde such that for every A, B, and C in the set X, this is going to look really familiar. A relates to A. Everything relates to itself. So this is, again, symmetry. Or no, reflexivity. A relates to B if and only if B relates to A. Symmetry. And then we have transitivity. If A relates to B and B relates to C, then A relates to C. Transitivity. So a relation on X is just a subset of X. It's a bunch of things we're claiming are related. It's some subset of that. So R is a subset of X. And these things are grouped together. We don't think of anything outside of this collection of X, this sub-collection of X. So let's look at a couple examples to understand this fully. Actually, let's look at it in one more way. So that's one perspective. A different way to look at it, to think about an equivalence relation, is consider the Cartesian product x cross x and let R be a subset of x cross x. Then, so this is a collection of ordered pairs. Does that make sense? These are ordered pairs. So remember what x cross x is. X cross x is just a bunch of ordered pairs, A, B, where A and B both come from x. So you could even draw a little picture. If you had x crossed with itself, and maybe x just is 1, 2, 4, 1, 2, 4, and then here's 1, 2, 4. The cross product x cross x is what? Can you take a minute and write that out? Draw the picture or write it out as set notation. What is x cross x? So look at okay, Penelope. Yeah. How many things are in x cross x? 9 things. It's just these ordered possible. It's all the combos of these things taken 2 at a time. So we're going to look at a collection of those dots. So my relation is going to be some subset of these things, and it's got to have certain properties to it. Then if, so R is a subset of that. How about this? Then we say A relates to A if A comma A is in that collection. We say A relates to B if A comma B is in that relation. So this guy right here is reflexivity. What do I need to say here? How do I phrase that this, if and only this, in terms of these ordered pairs? So A relates to, yeah, go ahead. BA has to be in there. So this right here, that if A comma B is in the relation, then B comma A has to be in there. This is the symmetry. And it tells us right away what kind of things we have to do. So first off, let's take a look. So this is reflexivity. This is our symmetry. What does reflexivity mean? It means that everything that has the same first and second coordinate has to be in R. So I'm going to include that, I'm going to include that, and I'm going to include that. I'm trying to set up an equivalence relation. That is what reflexivity looks like. Everything with first and second coordinates same is in there. What does this say? This says that if I put 2 comma 1 in there, what also has to be in there? 1 comma 2. So in other words, I have to be able to fold this thing down the diagonal and have it map back on itself. It has to be symmetric that way. So you see the symmetry in this picture as well, that it's symmetric around that diagonal. So if I put this in, that's got to be in there. But I don't have to put in everything. That's okay. Now lastly, we've got transitivity. So finally, could you take a minute and try to write out the transitivity in terms of these ordered pairs? Transitivity. And remember that was this, A and B B relates to C implies A relates to C. So remember this one here means that AB is in the relationship. Continue it down. Yeah. Cool. So let's take a look at this and see if we got it. If A relates to B and B relates to C, then A should relate to C. That means if A comma B is in there and B comma C is in there, then A comma C must be in there. Do I have an equivalence relation with what I've drawn, or is anything missing? I mean, there's clearly some things missing. Do they need to be added in?
You have one, for an example, you have 1, 2, and you have 2, 4.
Yep.
You also have 1, 4.
I need 1, 4 in there. Absolutely. Yes. Do you see that? Everybody see that? 1 comma 2 is in here. 2 comma 4 is in here. Or 2 comma 4 right there. So 1 comma 4 must be in there. I have to add that in. Otherwise, it's not an equivalence relation. And once 1 comma 4 is in there, what has to be in there? 4 comma 1. So this guy, in order to get an equivalence relation, I had to toss everything in. So they're all in the relation. Does that make some sense? Let me show you a really cool way to picture it besides this. So that's how I know I have an equivalence relation. What's another way? Well, it's with directed graphs. So here's how you can make a picture. This ordered pair definition is what our book gives us, but I really like this one as well. So let's say that on x equals a, b, c, d, we have an equivalence relation. And we'll call it tilde. And we're saying it's equivalence relation, so it's got all the things that we need, these three properties. Let's make dots representing each part of the set, A, B, C, and D. And let's think about what this, if we're going to think in terms of ordered pairs, I've got A, B, C, D, A, B, C, D. And then I've got 16 little points that represent all the possible ordered pairs. So if I was coming up with an equivalence relation using this picture, I'd start circling stuff and adding it in. What's in terms of reflexivity, what part of this collection of dots must be in there? The diagonal. The diagonal will always be in there. What does that look like here? So check this out. I'm going to use directed graphs. And if A relates to B, I'm going to take the A and the B and connect them with an directed line. So what does the reflexivity mean? It means everybody is connected to themselves. So that's reflexivity. Everyone is paired up with themselves. Now let's start adding some stuff in. If I have A relates to B, so right there's A relates to B, what else do I have to have instantly? Backwards, right? I got to have it the other way. It has to flow both ways. So I instantly have to have a double directed connection. So this is symmetry. So that's like coming over here and saying, okay, I'm going to toss, let's see, I'm putting in all these guys. Now they don't necessarily all have to be in there, but we're definitely just making sure they are for this example. And then to have A relates to B means I'm going to put that in there, and then B relates to A, that guy's in there. And then let's add one more. Right now, we could actually stop, I think. We could stop. This is enough right here, because even though I only have two things that are linked up, I still have transitivity, because if A relates to B, the only thing B could relate back to is A, right? There's nothing else for B to relate to because I haven't connected it to anything. So if A relates to B, the only thing B relates to is A. And look, what does transitivity say? That would mean that A has to relate to A, and definitely I got that. So if I've got this and this, I've already got that. If I didn't have that, well, then A wouldn't be related to itself anyway, and this would fail. So I definitely need to have that guy in there. But notice that B is not related to C or D, similarly for A or C. So these two guys aren't going to mix at all. I have an equivalence relation right here. But let's push it. Let's make it bigger. It's very minimal. What if I instantly said, okay, but hold on, I kind of want B to relate to D. And now you know what I have to add, right? I have to add the back arrow because these two must relate in different orders. What has to happen now? I've got to connect these guys because I've got a bridge already between them through another pet friend. So now I've got to connect A to D, and then instantly then I got to have D to A. But C's cool. C's like, there's no bridge to C that I have to worry about. So I've got an equivalence relation right here. So this is how you can draw a picture of your equivalence relations and kind of help you just think, do I have a relationship? And it just helps you to work with it. So let me stop. Is there any questions on the example? Because I want to say something heavier about it. Notice that what I'm saying at this point is that this and this and this are the same. They are equivalent. Once I have an equivalent relation, I'm saying if A is equivalent to B, these are the same thing. You can use them interchangeably. Pick your favorite. So these three things now are just one thing. And this is a guy on its own over here. So what I've done is I have partitioned the relation into distinct sets. How about we partitioned the set? Because in the set, A, B, and D are now all equivalent. A is equivalent to B is equivalent to D. That shit's all the same. And then good old C is just kind of a loner out here. So what I've done is I've created a set that really only has two things in it now. This group of stuff and that dude there. Let's get a more concrete example because that is all very, very abstract. So let's do something very solid together. And you can let me know if this is one of the homework problems because I don't necessarily want to do it completely for you. For sure. Did I give you the problem where x1, y1 is equivalent to x2, y2 if x1 squared plus, did I give you that one? Is that the one you got? X1 squared plus y1 squared equals x2 squared plus y2 squared? I didn't give you that one. Good, awesome, great. So we're going to say, so we're going to let our set X be the real plane. And we're going to think about X cross X, R cross R. So we're actually, so our space X, sorry, is R cross R. It's the plane. And I'm going to pick points in the plane, and I'm going to say that this point